Okay, so this is question 52, the last question in the fields and the capacitance homework booklet. So, question 52, part A. First of all, asks you to state three factors on which the capacitance of a parallel plate capacitor depends. So, the way that you can calculate the capacitance of a parallel plate capacitor is with this equation. So this is the capacitance, so it depends upon this A. So A is the area of overlap of the plates. So that's the first thing that I wrote down here. Epsilon naught is the permittivity of free space. Epsilon r is the relative permittivity. So basically, the material that's between the plates gives you this particular number, and then d, this is the separation between the plates. So if you write all three of those down, you get 2 marks. So you could, you could potentially, so any of those four things would do: the area of overlap of the plates, the separation of the plates, the dielectric between the plates, and also permittivity of free space. You get 1 mark for one if you get one right, and then if you get all three right, you get 2 marks. So in part B, again, we've got a circuit that is shown for measuring the capacitance of a capacitor. So this is one way that you can calculate the capacitance of a capacitor. We've got a source of potential difference here, and in series with that we've got a capacitor, and then if you flip the switch over to S2, then the capacitor would discharge and through this particular ammeter, and this ammeter's got a resistance. This resistance is 1000 ohms. Now this switch is a special type of switch. So this switch is driven by a signal generator, and it oscillates between S1 and S2 with a certain frequency. So the signal generator makes it go over to S2 and then back in a certain amount of time. When the switch is in position S1, the capacitor will charge up until the potential difference equals the supply of the EMF. So in other words, it'll flick over to S1, and incredibly quickly this will have a potential difference of 12 volts. When the switch moves over to S2, the capacitor discharges through this microammeter, and we're told to get here, so it reiterates that we've got a resistance of 1000 ohms. In one particular experiment, this capacitor, a 0.047 microfarad capacitor, is used with a 12 volt supply. So the very first thing we're asked to do is to calculate the charge stored on this capacitor when the switch is in S1. So that's fairly straightforward. We know the capacitance of the capacitor, we know the potential difference across it, so therefore to work out the charge we simply use this equation again. This is the capacitance of our capacitor, this is the potential difference, and when we multiply these together we get 5.64 times 10 to the minus 7. And again, basically everything's in terms of two significant figures, so we'll write this as 5.6 times 10 to the minus 7 coulombs. So we know how much charge is stored on this capacitor. For part 2, we're asked to calculate the time for which the switch must remain in contact with S2 so that the capacitor falls to 1% of its initial charge. So it's going to fall from 100% down to 1%. Now there's only one way we can do this, and that's by using this equation over here. So if you remember this equation, this is the charge at some time t. This is the starting charge. T is the amount of time that it takes to discharge by a certain amount. R is the resistance of the resistor that the capacitor is discharging through, and C is the capacitance of our capacitor. So the very first thing I normally do is I work out what the time constant is. In other words, I work out what RC is. It just simplifies the equation when I come to look at these exponentials. So RC is quite simply the resistance, 1000 ohms, multiplied by the capacitance, 0.047 times 10 to the minus 6. And if I do that, I get basically 4.7 times 10 to the minus 5 seconds. Now, that's the amount of time it takes to fall down to 37% or 36.8% of its initial value. That's not the time that I want. What I now need to do is I need to take this equation and I need to work out the amount of time it takes to fall down to 1%. So basically 1% is the fraction when the charge divided by the starting charge is equal to 0.01. So if I do that, that's the fraction, basically that's the fraction of charge left. So Q over Q0 is 0.01, so I can basically substitute that straight into our equation. So 0.01 is equal to the exponential of minus t over RC, but RC I've worked out over here. And from that, I then have to rearrange this equation. So I'm going to take natural logs of both sides. So I've got the natural log of this side, 0.01, is equal to the natural log of e to this. Well, the natural log of e to the power of something just gives me the actual exponential part up here. So that's minus t over the time constant, the 4.7 times 10 to the minus 5. So now I've got a fairly simple equation. If I multiply both sides by 4.7 times 10 to the minus 5, I end up with this equation. And then it's just a matter of putting some numbers in my calculator. So the amount of time it takes to fall to 1% of its initial value is 2.2 times 10 to the minus 4 seconds. So we're going to assume that the capacitor discharges all of its stored charge when it goes through the ammeter when the switch flicks over to that S2 position. And we want to calculate the current that this meter reads. Well, if you think about it, if it just flicked over once, the amount of charge that went through the ammeter would be this, because that's how much charge the capacitor holds when it's fully charged up. So if it simply flicked over to S2, this is how much charge would flow. But we don't want to know that. We will basically want to know the current, and that's the amount of charge that flows in 1 second. Now, this, we're told in the question up here that the frequency of this signal generator, which makes the switch flick backwards and forwards, is 400. Is basically 400 hertz. I told you that. So in other words, it flicks backwards and forwards 400 times in every second. So what that means is that this capacitor charges up and discharges 400 times every second. So actually what it does, in every second it will discharge 400 lots of this. So if it discharges once, this is how much charge will flow from the capacitor through the ammeter. If it discharged twice, it would, twice as much charge would flow through it, but it's actually discharging 400 times in every second. So if we talk about every second, then t is 1. So the total amount of charge is just 400 times that. So 400 times the 5.6 times 10 to the minus 7 divided by 1, which is the time, gives you 2.3 times 10 to the minus 4 amps. Now in terms of breaking marks down, in this particular question for part B, basically in this part, if you write down that Q is equal to CV, and you put the right numbers in the equation, that's 1 mark. And then if you write down 5, and then if you calculate that correctly, that's a 2nd mark. For part 2, this part over here, if you work out the time constant correctly somewhere in your answer, then you get 1 mark. If you have this equation written down somewhere, that's your 2nd mark, and then your final mark is for your actual answer. So that's 5 marks altogether. And then your final mark is basically just for doing this. So it's multiplying the charge that you worked out in part 1 by 400, and that gives you your total current that flows through your ammeter. So that gives you the 6 marks that you've got. So that's all of the end of the questions for the electric fields and the capacitors homework booklet. So that was question number 52.